Welcome all. I'm Sandeep Kiran, PhD student at Stony Brook University. Today I'll be talking about our work on INVISILINE, Invisible, Plausibly Deniable Storage. This work is in joint collaboration with Professor Bogdan from Florida International University, Andan from UIC, and my advisor, Professor Radu Sayan. Encryption has been the de facto solution for protecting the data at rest. But is that really sufficient? Well, not until the bad guys have access to the decryption keys. As you can see in this famous crypto cartoon, you don't have to break the encryption scheme. All you have to do is to mount a rubber hose attack where the user is continuously hit until he or she reveals the password. It's not always the bad guys. The governments and authorities are equipped with laws by which they can force users to reveal their sensitive data. For example, UK's RIPA Act can label you as a criminal if you refuse to give the password. Same is the case with US's Cloud Act and Australia's Assistance and Access Act. There have been many real-life instances where governments, in the name of national security, law enforcement, investigation, have resorted to such coercive tactics. For example, recently the US government has empowered the customs and border protection agents to thoroughly and freely check users' phones and laptops. I hope I was able to convince you that mere encryption of data is not sufficient against these powerful adversaries. What we instead need is a mechanism by which users can deny possessing any sensitive data or can deny involving in making any sensitive transaction even when there is heightened scrutiny and suspicion. That's plausible deniability. With PD, the investigating authorities cannot prove that the user is hiding any sensitive information even though the user is actually doing so. A very simple PD mechanism is a one-time pad. Given a ciphertext, I can always come up with a key that decrypts the ciphertext to a benign plaintext. To the adversary, I would give the benign key, and to the actual user, I would give the true key. Deniability is not obfuscation. The adversary has complete access to the user device. The adversary knows what software is installed on the device, what binaries are running. The goal of the PD system is to ensure that the adversary cannot find out that the user is actually using such software. For every runtime action that the adversary sees, there has to be an alternate plausible explanation. Let's now look at the adversary. The goal of the adversary is to find out if the user is hiding any sensitive information. The adversary knows the complete system design. We are not talking about security through obscurity. The adversary can force the user to disclose the secret keys. We already talked about it. The adversary can either be a single snapshot adversary, which can capture a single snapshot of the device, or it can be a multi-snapshot adversary where it can take multiple snapshots of the device at different points in time. It can save these snapshots, compare them, and see if there's any pattern that indicates hidden data. But most importantly, the adversary can question why the user is running the PD software on the system. The primary goal of any PD system is to hide data. Let me give you an example. One of the popular PD systems in the early 2000s was TrueCrypt. TrueCrypt was a disk encryption software and also had a mode which allowed the user to store hidden data. So if the user had TrueCrypt installed on the device and is trying to cross the border, there's every reason for the border guy to be suspicious, even though the user is not hiding any data. But on the other hand, if the user uses a non-PD disk encryption software, for example, BitLocker for Windows, there's no reason to be suspicious. Some more assumptions about the adversary. The adversary is assumed to be computationally bounded. It does not have infinite resources. The adversary does not have access to the runtime system state, for example, DRAM and caches, and it is assumed to be rational. If upon revealing the keys, the adversary finds no proof of any hidden sensitive data, it would not persist further. Let's now look at what an invisible PD system is. But before that, public data is the encrypted data which the user is willing to disclose under coercion. Hidden data is the actual data that the user wants to conceal from the adversary. We say that a PD system is invisible if it satisfies these criteria. The operations on the public data should not be needing the PD software. Hidden data, of course, uses the PD software. Why is this important? Again, going back to our previous example, The user would not want to have TrueCrypt installed on the device when crossing the border, because that raises suspicion. But instead, upon coercion, if the user can reveal just the public data, hide the hidden data, just the public data using a non-PD disk encryption software like BitLocker for Windows, there's no reason to be suspicious. Secondly, storing hidden data on the disk should not result in saving any additional metadata on the disk. It should not result in any non-standard disk layout, because these are clear signs for the adversary that the user is trying to hide some data. We have investigated the prior PD systems and categorized them to see if they are multi-snapshot adversary resistant and also if they are invisible. As you can see, other than Infuse, rest of the PD systems do not satisfy both the properties. But Infuse actually needs modification to the flash translation layer, and as you're aware, most vendors do not expose their FTL layer outside. INVISILINE supports both properties. It is resistant to multi-snapshot adversaries and is also invisible. So quick overview about INVISILINE. We talked about INVISILINE is the first invisible PD system with no media dependencies. INVISILINE achieves invisibility by having disk layout and encoding which is compatible with the open source disk encryption software DMCrypt. INVISILINE stores hidden data in the initialization vectors that is used for encrypting the public data. Since the hidden data goes in the IVs of public sectors, any updates to the hidden data can plausibly be explained as changes to the randomness that is used for encrypting the public data. Before we move into the details of INVISILINE, let's quickly understand what DMCrypt and DM integrity is. DMCrypt, as we all know, is a disk encryption software. It's a device mapper target that provides confidentiality services. Device Mapper is a Linux kernel framework that maps physical block devices to logical block devices. Each of these device mapper target provides a specific functionality. For example, DMCrypt provides integrity services, DMCrypt provides confidentiality services. You can stack these logical block devices one on top of the other, each providing a specific service to the layer above it. And on top of all these logical block devices, you can have your file system mounted. DMCrypt and DM integrity can be set up using a tool called Crypt Setup. Crypt Setup takes a physical block device and exposes two logical block devices, one for DMCrypt, one for DM integrity. Crypt Setup supports multiple IV modes. IV modes indicate how the IV used for encrypting the data is generated. INVISILINE relies on the random IV mode. Let's now look at the disk layout in case of a random IV mode. When the file system wants to encrypt a particular sector, it sends the sector data to DMCrypt. DMCrypt generates a new random IV. It encrypts this sector's data with this IV, and it passes on the IV and the encrypted data to the underlying DM integrity logical block device. DM integrity saves the IV and the data so that when the file system wants to read the data, DMCrypt gets the IV and data, decrypts it, and sends back the clear text to the file system. Coming to the layout, at the bottommost layer, you can see the physical block device with all the sectors. DM integrity logical block device separates the sectors into data sectors and metadata sectors. Data sectors hold the actual encrypted data. Metadata sectors hold the IVs for these data sectors. Here's INVISILINE's architecture. INVISILINE adds one additional software component to the DMCrypt module. We call it as DMCrypt Hidden. DMCrypt Hidden manages the hidden data which goes into the integrity metadata sectors. INVISILINE also exposes one additional logical block device in addition to the two that already come up with the default Crypt setup. This additional logical block device is the hidden block device on top of which you can mount your hidden file system. It is important to note that for the same physical block device, we can now mount two file systems, one for the hidden data and one for the public data. Okay, so a user session is the explicit time interval during which the user works on both public data and the hidden data. So at the start of the session, the user installs INVISILINE, then works on storing both hidden and public data. At the end of the session, the user uninstalls INVISILINE and installs the vanilla decrypt. Logical sectors are the sectors pertaining to the file system. Physical sectors are related to the block device. So if you look at the public world, the size of each logical sector is same as the size of the physical sector. Whereas coming to the hidden world, since the hidden data is stored in the IVs of public sectors and the IV size is 16 bytes, it takes 32 IVs to store one logical hidden sector of size 12 bytes. We term this factor as the storage factor. Remember this diagram, we have the sector that holds the encrypted public data, and in the corresponding IV we store the hidden data. So this kind of setup brings in additional properties and implications. One is hidden data non-interference. Remember we talked about encrypt generating a new IV for encrypting the public data every time. If a sector's IV already holds hidden data, and if a new random IV is generated, it would overwrite the already existing hidden data. Security non-interference, again, if the sector's IV contains hidden data, and now if you want to update the public data in the sector, you cannot reuse the same IV to encrypt the new public data, because reusing IV is not a good security practice. Explainable re-encryption, again if the sector's IV contains hidden data, and now this time if you want to update the hidden data within the IV, you cannot simply update the hidden data and then use the new IV to re-encrypt the existing public data, because any multi-snapshot adversary who's looking at this sector can easily figure out that you are re-encrypting the same public data without any change. What the third property also implies that any updates to the hidden data should always be tagged along updates to the public data. What this also means is that you cannot statically map logical hidden sectors to physical sectors. You should have some kind of mapping table between the logical sectors and the physical sectors. What this means in terms of implementation is that we now have a free list that tracks all the modified sectors within the session. These are the sectors where future hidden data can be stored. We also have a version number associated with each logical hidden sector. This gets incremented on each hidden update. Remember we talked about security non-interference. We now also have a public write counter associated with the hidden data. This counter gets incremented on every public write to the same sector whose IV contains the latest. We also talked about having a translation table that maps logical hidden sectors to physical sectors. Where do we store this translation table? A couple of options. Store the translation table at a fixed offset within the metadata sectors. The disadvantage with such an approach is that on every update to the hidden data, there's also change happening to the translation table, and an adversary might easily detect it. Instead, in INVISILINE, what we use is called as a reverse map, wherein we store the logical hidden sector number along with the hidden data. So how do we initialize this table? During startup, we read all the metadata sectors, we extract the logical hidden sector number and also the physical sector number and add it to the translation table. We also take care of the version number to avoid any stale data. Given all these fields, here's what the IV looks like. In addition to the hidden data, you also have the logical hidden sector number, the version number, the PWC, etc. What this means is that instead of saving the hidden data in the entire 16 bytes IV, we can only save the hidden data in certain number of bytes. What this also means is that the storage factor, which was, remember we talked about storage factor being 32 earlier, it has now increased to 52. This means that in order to store one logical hidden sector, we would need the IVs of 52 public sectors. Let's look at INVISINGLE. INVISINGLE is INVISILINE's optimization for single snapshot adversaries. If you remember, a single snapshot adversary can take a snapshot of the device at most once. Given this, we can get rid of the translation table, the free list, etc. because we can now map logical hidden sectors statically to physical sectors. For example, logical hidden sector I always maps to the F physical sectors from I into F to I plus 1 into F. To an adversary, it would still not be able to distinguish the IVs containing hidden data and the IVs containing random data. Since there's no ATM, there's no free list, and there's a reduced storage factor, INVISINGLE is much faster than INVISILINE. Coming to the evaluation, we evaluated INVISILINE and INVISINGLE by making changes to the Linux kernel 5.19. Predominantly, the changes were made to the DMCrypt module. We also had changes to the crypt setup tool. The experiments were run on Core i7 machine with 6 cores, 16 GB RAM. We used flexible IO tester to capture the performance metrics. We captured the throughput with vanilla DMCrypt and compared it against INVISILINE and INVISINGLE, both for sequential workloads and random workloads. Public reads with INVISILINE are almost similar to the values achieved with the vanilla DMCrypt because reads do not have any additional overheads. Public writes, on the other hand, are comparatively slower with INVISILINE. That's because on every public write, INVISILINE checks if the sector's IV already holds hidden data or not. Hidden operations with INVISILINE are much slower than the public operations because of the storage factor. INVISILINE, as we discussed earlier, INVISINGLE, as we discussed earlier, is much faster than INVISILINE. So in conclusion, we discussed why plausible deniability is needed. We discussed the need for invisible PD storage systems. We introduced INVISILINE that stores the hidden data in the IVs of public sectors used in DMCrypt. INVISILINE achieves a throughput of 4.5 Mbps for hidden data, and INVISILINE enables you to store around 19 GB hidden data on a 1 TB disk. You can find the source code of INVISILINE at this location. I'd encourage you to read the paper for any additional details. Thank you.